So the problem says, suppose 40 joules of energy is transferred by heat to a system while the system does 10 joules of work. Later, heat transfers 25 joules out of the system while 4 joules of work is done on the system. What is the net change in the system's internal energy? Now, we've talked about this, but it was about 2 weeks ago, and it's coming back again. So this, remember, you may not remember, we talked about the laws of thermodynamics. What do you remember for the laws of thermodynamics?
Energy cannot be created or destroyed.
And that is the one we're using here. That's the first law of thermodynamics. You have the 0th law, which is if system A is in thermal equilibrium with system B, and system B is in thermal equilibrium with system C, then system A is in thermal equilibrium with system C, which has the fundamental outcome of if temperature A equals temperature B and temperature B equals temperature C, then temperature A equals temperature C, which is, it seems ridiculously simple, which is why it's the 0th one, because after they come up with some laws, they're like, oh, this wasn't as obvious as it seemed. Then we have the first law, which Ashley just said, energy can't be created or destroyed. And I'm just going to say I'm not an English professor, so I said cannot and or, right? We write that in equation as the change in internal energy. So delta U is change in internal energy is equal to the heat added to the system So I'm being very explicit here, added to, and I know it's hard to read my 2 there, that's better, minus the work done by the system. So the change in internal energy of the system is equal to heat added to the system minus the work done by. That is, work done by the system is energy going out. Heat added to the system is energy coming in. So that's why the signs are plus and minus. As I said in class, you will find situations where a textbook will make them both plus signs, and work, instead of being work done by the system, it's work done on the system, because then it's energy coming in, right? So you have to pay attention and know actually what the basis is, that its energy can't be created or destroyed. And then the equation makes sense. Okay, just for completeness, the second law has all kinds of different statements. The one that I used in class initially was that heat spontaneously flows from hot to cold. Not from cold to hot. It's the one law in physics that tells you the direction something's going to have to go. And there are lots of different statements of it. And the third law is the simplest of the laws, really. Third law is nothing can reach absolute zero.
Challenge accepted.
Challenge accepted. There are people who have come extremely close, but that law is considered an immutable law. Okay, so we are going to do, like I said, we're just going to solve this using what Ashley said. The change in energy of the system is equal to the heat added minus the work done by. So now looking at the problem, we have 40 joules of energy is transferred by heat to the system. So that is a heat. Is it added or taken out?
To the system?
Yep.
Isn't that added?
Okay, so that's heat added. And then we have the system does 10 joules of work.
Work done by.
So that's work done by. Excellent. So those are the two things that we put in here. So we would have change in internal energy, and I'm going to put subscript 1 because we have later, so that's going to be subscript 2's, is equal to the heat added, 40.0 joules, 00 joules, minus the work done by 10.00 joules. So that's 30.00 joules increase is the change in internal energy originally. And then later we have heat transfers 25 joules out. So that's going to be Q added equals what?
Isn't it negative?
Yep. While 4 joules of work is done by the system, or excuse me, not done by, done on the system. The wording here is kind of odd. While 4 joules is done by work on the system. I would have said why 4 joules of work is done on the system is how I would have rearranged those words. So that's going to be work done by is equal to minus because that was done on the system.
So then we would end up just adding.
And so I'm going to have delta U2 is equal to minus 25.00 joules because I had heat flowing out, and then minus parenthesis minus, there we go, minus 4.00 joules because that was work done by the system, not work done, or excuse me.
It was work done on the system.
Yeah, that was work done on the system. And so it was minus work done by. So we put that together, and that's equal to minus 21.00 joules. And so our net work, or our net change in internal energy, is 9.00 joules. Or as my funny teacher in graduate school said, jowls. Because he was funny. Okay, now the next one, that question and the next one, of course, these are both based on stuff that we're going to be lecturing on probably today.
Okay.
The next one, you really don't have the background to answer at this point. The next one is, actually, I did need to do this, but too late now. Fortunately, it didn't crash.
I can move.
Which equation represents the net work done by a system in a cyclic process? You haven't seen that at all, right? So I can still go ahead and answer that. It's just stuff that we're going to see in a minute here, or in a minute, in an hour and a half. We like to show our thermodynamic processes on a pressure versus volume graph. And so when we do pressure versus volume graph, we might have a cyclical process is one that starts and ends at the same place. So it could go clockwise or counterclockwise, and you have to determine which way it's going. Now, things we haven't learned yet, right? First one, we've already had the stuff. Here we have it. Work in thermodynamics. Of course, what is work as far as you know right now?
Distance times.
Okay, mostly right. It's force dot. Dot means parallel. So it's force times the distance parallel. So to get this from what you already know to thermodynamic case, we take the example of a piston. You have a piston Okay, so there's a box, a piston, and that piston has a plunger in there. And we're going to make this plunger go down. So we're going to apply a force on the plunger, and it's going to move some distance delta x. So if I want to find the work done here, the distance is parallel to the force, right?
Mhm.
And so my work would just be the force times delta x.
Pause. Why is it parallel?
Because my
For the
force
same
is
reason.
down and my arrow for the delta
Just
x
the
is
arrow.
down.
Power.
Right, this here is the same direction as that. And so those are parallel. They're in the same direction.
Okay.
And so the work is just force delta x. But now we want to put this in thermodynamic terms. So we have the force applied over a piston of some area A. And so the force relates to pressure, right? We know that we're going to have pressure inside that is making a force equal to pressure times area on that surface. And so if we're moving at equilibrium, that is, it's at a constant speed, so the force up and force down the same, no acceleration, then the force is pressure times area. And so this is, the work is pressure times area times delta x. But area times delta x is the change in volume. And so the work is equal to pressure times change in volume. Now, this is not the rigorous proof. This is a specific case proof, but it turns out that it's always correct. So the thermodynamic work is pressure times change in volume. So if we look at this, if we go from the places that I've just labeled A and B, how can I calculate the work there? It's constant pressure. So how do I calculate the work?
The volume displacement.
Okay, we have, this is my VA, this is my VB. Pressure A and pressure B, of course. If I name this one C, then I can put this as pressure C. So if I want to find the work, what is it going to be?
Pressure times volume.
Which pressure?
A.
Okay, pressure A times, and what do you say for volume?
A.
Mm-mm. It's the work going from A to B, so it's going to be change in volume, so it'd be VB minus VA. Now on that graph, that represents an area of everything under the line, right? Because that, if you make a rectangle here, the height is pressure A and the width is VB minus VA. So the area under that line is the work. And that's always true. If I have a pressure volume graph, the area under the curve is the work done. Since it was going to the right, it's a positive work because it was expanding. If it expands, then the system is doing work on the environment. If it contracts, then the environment's doing work on it. So now we look at this and we say, what about the work from B to C? What's that going to be?
PB. Is that A or B?
On top is A, on the bottom is B. Or C, I mean.
Okay, so A now PC minus PA.
Okay, this is a very important distinction. This is not change in pressure, it's pressure. If the pressure changes, what do you use, Ashley?
Poisson's.
You have to use an integral to add it up because of the change in pressure. You know what you guys don't do?
Calculus.
Yeah, you don't do calculus. But look at the other part of this. So if you have a changing pressure, all you have to work with is find the area under the graph if you're one of you two, until I give you other equations. You can do it with calculus, but it's pressure times change in volume. What's the change in volume going from B to C? Nothing. And so that means the work there is nothing because there's no change in volume. What's the area under a vertical line? Nothing. Now we go from C to D. Now it's going back the other direction. So that's going to be work CD is equal to the pressure there, pressure C, times it ends at VA, it starts at VB.
So VA minus
And if we were to put that on the graph, that would be this area, right? So the work is going to be the area inside of that cycle. No matter what shape the cycle is, your cycle could be something that goes like this. If it's clockwise, then it's going to be positive work because the top part is above, or the expanding part is above the contracting part. So clockwise is positive. So clockwise is positive work. Let me make that plus a little clearer, plus sign. Maybe a little clearer. And it's just the area contained. So when I do a complete cycle, the work net is equal to the area inside the cycle. Now, that's not what the question is. That's part of how we understand this. So when you do a complete cycle, that's your net work. And then you have, well, what about your heat? There's nothing in what we did here that relates to heat, right? But we do have the first law that says change in internal energy is equal to Q minus W. And if we are at state A is going to always have the same energy. So if I start and end at the same place, what's my change in internal energy? Zero. Because you're at the same place, it's going to have the same energy. So for a cycle, delta U equals 0, and that gives us Q minus W equals 0. So Q equals W. And so the Q is heat added minus heat removed is equal to the work, which is what we've gone through. And so the term that they have is QH because at high temperature the heat goes in, minus Q cold because at cold temperature the heat goes out is equal to work. That's for a heat engine. You can actually reverse a heat engine and it still turns out to be the same equation. Okay, yeah, class started right now.